professor at the Courant Institute. He holds both the Max from Princeton and an MD degree, and he has various research in data science and machine learning, and also in medicine applications. And he's going to talk about ridge analysis and time frequency analysis for non-stationary time series.
Okay, so as soon as I can start.
Yeah.
Thank you very much for the invitation. It is my great pleasure to be here and share some of my recent research results. The topic is maybe to some extent out of the date, right? Nowadays, who doesn't talk about deep learning? Now, why am I here? Okay, there's no deep learning, so hopefully I won't disappoint you. So the topic is about time frequency analysis, and we want to do some ridge analysis. I'll explain to you why I do so, and how to do it, and what we know so far. And there are many open problems here. So the motivation today is a sensor, a type of biomedical signals called photoplethysmography. Photo means light. Plethysmo means volume. So it is a tool that you use light, for example, there's a light emission, okay, to measure the amount of volume inside your finger. So what you do is, not just finger, but other places or under the skin. What you have is you have a light emission, which and the light will go through your skin and reach your capillary. And inside the capillary, there is a hemoglobin. And the hemoglobin will carry different amount of blood, and it will absorb the light and reflect the light. And then you record the reflected light using photodiode, and you get some kind of signal. Okay, it contains a lot of information, but no matter what, it is how the signal looks like. You can see that it is kind of oscillatory, okay? And you can see some repetitive pattern. And from this repetitive pattern, actually, you can see a lot of small details that repeat itself. So this kind of repeated pattern will repeat itself roughly 1 second per cycle, which is about your heartbeat. So your heartbeat beats about 1 second, okay, every 1 second. And you can see this morphology actually captures your hemodynamic features and so on. And this is some kind of signal that we consider high quality. You can see some kind of patterns, right? It's oscillatory, kind of regular, and it is, well, something. Okay. The focus today is not digging into this morphology and telling you, hey, how to get information for this one, for this kind of signal and study biomedical problems. Instead, I want to ask you a very simple question. Based on all the introduction I gave you, and maybe you have worked on this kind of signals before, you may have some feelings. Okay, so I give you 2 signals that are recorded. And at least one of them is of high quality, so-called high quality, so-called high quality. Okay, which one is of high quality? If I ask you, what do you think? Which one is of high quality? Okay, usually if someone answered, it will be the second one. Why? Because the second one is more kind of regular, right? It repeated itself, blah, blah, blah. Yes, you are right. These 2 channels, these 2 recordings have been labeled by experts, physicians. And they said, this one is good. This one is garbage. That is experts' opinion. Okay, and the question today is to answer or to study is it true? How to quantify it? What do you mean by signal quality? And so on. Okay, and so I'll come back to this question in the very end of the talk. But before I go into details, let's have a quick recall, which if you have any experience in signal processing, you know it. What do we do for a given signal, a time series? Usually, the first mission is going to visualize the dynamics. You can plot the signal, or you try to generate spectrogram, right? or there are some other ways you can visualize things, no matter what, visualization. Second, you may want to estimate the source of number. The number of sources and so on, and do decomposition, do denoise, and so on. Then, after a second go, you may want to extract dynamics for each component and do change point detection, estimation problem, and so on. You can even try to do a prediction or control forecasting. So there are several basic questions you want. In particular, you want to do maybe uncertainty quantification because nothing is noise-free, and you always have noise. You always have model uncertainty. So how to quantify it so that you can answer scientific questions? How certain is your answer to this scientific to this data set analysis? Obviously, it is impossible for me to cover everything in 15 minutes, even if I want. I mean, it will be a disaster. So today I will only focus on one topic, and which is try to extract dynamics of each component. And there have been some literature, which some have been published, some are under review, and so on. This actually just submitted, you see, December 31st last year. So it's very fresh, and well, anyways. Okay, so that is the kind of the problem, medical problem at hand. And this is usually the mission and overall structure. And this is where I will target. So I give you a very quick summary of this kind of mission if I want to achieve, and how to use the time frequency analysis approach. So on the top, that is a time series. And the gray line is the noisy signal, which is a simulated one, simulated by me. So I know the ground truth. The red one is a clean data, original data. Okay. And then I run time frequency analysis and get this time frequency representation. What is time frequency analysis, by the way, right? Some of you may know it, some of you may not hear about it. So time frequency analysis, the idea is very simple. It is essentially a divide and conquer approach to do signal processing. Because the signal we encounter is usually non-stationary. So what you assume is every locally you have to define mathematically, right? But suppose you have a good definition, locally is like stationary. So locally, once you get it, you can try to understand its spectral structure. For example, using Fourier transform or so on. There are many variations, but no matter what, it will give you a picture like this called time frequency representation. This is the time, this is frequency. So at each time, if you look at the y-axis, it has some kind of intensity, which indicates how strong the oscillation is and how fast it oscillates. For example, there is a curve here that you can see, right? This intense curve suggests that, for example, at time 25, the signal, this component oscillates about 15 times per second. That is how you reach the time frequency representation. Okay, so this is a very quick 30 seconds introduction of time frequency analysis. Usually our goal is to go through this time frequency representation as an image and try to extract as much useful information as possible. So next step, usually you can do something else. Some people try to say, okay, I have an image, so CNN is a good friend, so go. Yeah, that's not what I will do. I will just go through the path saying, okay, we want to extract reach. And what is reach? Okay, that's what I will introduce. But what I show you here is, you can see there is a blue dash. Those dashes are the reach that you can visually identify. And that is how it looks like, reach extraction. Once you get reach, okay, you can apply some, for example, nonlinear optimization problem. This is a nonlinear optimization problem called SAMD, shape adaptive mode decomposition. I will not discuss it today. Okay, but once you run through this nonlinear optimization problem, you can recover each component. So here in this plot, the red curve is the ground truth. I have two components inside. There are two sources. Each one oscillates in different ways. Okay, and the blue curves are what I recover from the noisy signal. And once you get to the reconstruction, then you can continue to do other signal processing goals. Just like I mentioned, how to understand the dynamics and so on, forecasting, uncertainty quantification, etc. And the focus is again, what is rich, how to define and extract it. Okay, that's the overall goal. So the plan of today's talk will be what is rich. I'll give you some theoretical justification, and then I will give you some algorithms about how to get ridges. And then you will see some clinical results. And on the way, I will tell you some open problems, which I don't know, it's kind of challenging to me even nowadays. So let's start with a model, because we want to study ridges of time frequency analysis. So we need some model. And usually the focus of time frequency analysis is something oscillatory. And that is actually the very original motivation of this set of work. That is, most of biomedical signals are oscillatory. And it oscillates with time-varying frequency, time-varying amplitude, and the noise. And there may be also trend. So the model we consider is this algebraic model. You have Y, which is a random process. And this random process is composed of K oscillatory components, AI of t cosine, 2 pi phi of t, and the T, which is trend, and the phi, which is a random process, mean zero random process. Let's take a look at each component. I will assume that AI is amplitude modulation, which is positive function, and it is regular, C1, and it changes slowly. And the technical details are right on the right-hand side. This is what it means by oscillate slowly. And you have phi. Phi is a monotonically increasing function, which describes the behavior of the system so that phi prime is a positive function, which also changes slowly in the following sense, which describes the instantaneous frequency. If you think about this model, this AI of t cosine 2 pi phi of t, this is we call intrinsic mode type function. Now, you can imagine, suppose AI of t is a positive constant. Phi of t is a linear function. For example, 2 pi phi prime of t. Then this is a harmonic function, right? This is harmonic, which you can easily analyze using Fourier transform. But right now, I tell you that it is not so. The amplitude and the frequency both are changing. Then how to do the analysis? That will be the challenge. And the T is a trend, which we assume to change locally. And mathematically, it can be quantified by just do Fourier transform, like in the distribution sense, and you consider support, which is next to zero, which means it just changes slowly. Okay, that is the definition. Trend. And you have phi, which is noise. And you have usually we assume mean. Mean is zero. You can be stationary or not. It can be non-stationary, can satisfy something crazy if you like. But in this talk, we will focus on stationary thing to simplify the discussion. And the mission is, I have this kind of random process. I give you one realization only. Could you please decompose A, phi, T, phi, everything for me, even give me the statistics of phi? That is the mathematical question we usually encounter in time frequency analysis. You can certainly further model every component like A, phi, make them random process satisfying some properties that you want to estimate. You can do it, but that is not the focus today. So today, the oscillatory part will be deterministic. The random part will be stationary, even Gaussian. That will be the model we consider today. Okay, so with that model, we can start to consider what ridge is. What is ridge? And I have shown you some pictures and mentioned the word like synchronous squeezing transform. But there is a transform that is too nonlinear. Even nowadays, we don't know how to do the analysis. So I will step back and to show you the magnificence of this kind of the challenge of this problem by just using a linear type time frequency representation, which is in general just nothing but a convolution. So wearable transform, in particular, continuous wearable transform WF of a function f is defined in this way. You have an f of tau, and you convolve it with psi. And psi is something called mother wavelength, which definition I will give you more precise definition, but you just imagine it is something oscillatory. In the frequency domain, it is 0 at frequency 0. It has some decay to 0, and it is kind of relatively well supported. So that it is a very nice function. So you just convolve with some function f with some wavelengths, mother wavelengths. And when you do the convolution, you dilate s, you dilate psi, you do some dilation. Okay, that is a continuous wearable transform. Once you get it at different time and a different scale s, you take square and take square, absolute value and square. That is people call scalable. Okay, and you can imagine to study this kind of signal, you need some regularities, conditions, growing conditions. Usually, we just consider f to be a temporal distribution. Psi is a Strauss function, and everything's fine. Then you can do things, or you can slightly reduce the regularity of psi and slightly increase regularity of f, growth, and whatever. There are several things you can balance. And now let me show you some example of how this kind of time frequency analysis looks like. So this is a signal, ft, where I just assume amplitude is 1 for simplicity, but phi, I have time varying frequency. So that you can see it oscillates slowly here and fast here, right? And gets slow again, get fast again. So this is some kind of signal with time varying frequency. And this is the three-dimensional picture of the continuous wearable transform. This is time, this is scale, and you can see that at some point, you can see some kind of mountain, okay, some mountain, some kind of mountain or some bumps at each time. And you can convert it, you can just shift it, okay, just view it from the top, so that you get the time frequency representation, which is an image. And here I superimpose the so-called instantaneous frequency phi prime on top of it, so that you can see there seems to be some very close relationship in between the idea of reach, which is a local maxima here, and the instantaneous frequency. That's very intuitive. Okay, so we can start to do some analysis. Let's say, suppose we have some adaptive harmonic function with m components. And we made some assumptions. For example, the frequencies do not overlap, and so on. There are some sufficient separation, and so on. Some technical, small, mild assumptions. And then you do some Fourier transform. You do, continuous wearable transform, WF. You can write it on the right-hand side, which if you take a look, and based on the assumption, it is kind of something relatively easy to see. Why? Because the function, the signal, the adaptive harmonic function signal, it has time varying frequency and amplitude, but frequency and amplitude doesn't change too fast. So locally, you can use Taylor expansion to represent the amplitude and frequency. Okay, and once you use Taylor expansion, you have some polynomial terms. And then because the window you use here is a wavelet, which is kind of compactly supported and smooth, so you can well control its behavior with some small errors. And assuming that the signal itself is harmonic at that time, and now this guy is nothing but a Fourier transform of the wavelet. So you immediately get everything. And now if you make an assumption saying that, oh, epsilon is sufficiently small or error is sufficiently small, which holds in many practical situations, then you get some well approximation by removing the epsilon e term. And if psi hat is compactly supported and the frequencies of different components are well separated, then you can rewrite things in this way. You get several summation of each component. And that is what the picture you get when M is 1. What you see is, well, in the end of the day, there will be a bump because psi hat Waverly transform in the frequency domain has a bump shape, okay, and it will have maximal value at the scale that is inverse to the frequency, and it is weighted by amplitude modulation. That is the picture, how you get the picture. So from this picture and from this very quick derivation, you may consider the following definition of reach when you are working with time frequency representation. You can say, okay, in the end of the day, we just want to find local maxima, right? So you just define it. The R1 condition is at each time t, on the scale domain, you try to find a critical point such that this critical point is local maxima. That is it. And we make an assumption that, okay, suppose you can find it, then all the point at all time should be regular C1 because it's smooth. So yeah, that is the definition you can put. And in practice, we just take this assumption, this definition, and try to do the local maxima. Find local maxima, okay? And then you just hope for the best. No matter what, this is kind of something you can consider. And luckily, in this case, when there is no noise, you only have a deterministic signal, then, well, things becomes quite good. By the derivation I gave you in the last slide, actually this SF, the reach SF is roughly approximate to the psi hat of 2 pi s v prime, so that this is reversed to the instantaneous frequency. And you can also show SF of t is actually C1. And you can see from that definition, right? It is derivation in the scale domain, and you want to get C1 in the time domain. Clearly, you see that is implicit function theory. So we just use implicit function theory to show C1. And by the argument in the previous slide, you can see that the reach is roughly the instantaneous frequency. So which tells you that, good, in this very, very simple setup, you only have one component that is oscillatory, okay, but with time varying frequency and even amplitude. In the end of the day, the reach can be determined by local maxima at each time. Second, the reach gives you the instantaneous frequency information. So that is the support of why time frequency analysis can be useful to study time signals with time varying oscillation and with time varying frequency and amplitude. But the situation starts to get more complicated. Yes? Yes. Scale. In the y-axis, it is scale. In the continuous Waverly transform, we consider time and the scale. And then I show you here that the scale actually is reversely proportional to the instantaneous frequency. Okay, so what you get here, okay, this is time scale, but I reverse it in order. This is scale from big to small. Scale from small to big. Okay, and the small scale indicates high frequency. Okay, and the high scale indicates low frequency. And it is intuitive in the following way. You have something oscillatory. If I stretch it to be very, very long, you can imagine that its frequency is actually very, very low. But if I squeeze it to be very, very short, oscillate, then it oscillates very, very fast. Okay? Good. Okay, just a kind of a very quick remind, because you have heard me so far, and you haven't fallen into sleep. So you may have a feeling that, look, reach, this term is so common, right? We have heard a lot about it in statistics. There's a ridge analysis in statistics, a huge literature back in 1980, even earlier. Okay, and many big names attached to this field. So what is the difference? Why don't you just use existing literature to study ridges in time frequency analysis? Okay, why? The main reason is, well, the focuses are actually different. First, in our application, the ridge formation mechanism is very important. We want to understand how the time frequency representation is generated. But in statistical literature, usually the data is given. This is already formed, and you want to understand how to define the ridge and estimate it. So this is the first difference. Second, in our study, it is time frequency analysis. So time information is very important. We need to know temporal information. Temporal information needs to be taken into account. But look at this kind of picture or MRI, there's no time information. So somehow it's a pure image. Everything is on 2D. Okay, this is a kind of cosmology application. They want to determine what the ridge is. So, or even fit the ridge. Okay, so there is no temporal information that is taken into account. So we need a ridge to be a function of time. Third, the noise impact on ridge is via different mechanisms. The noise in our application is from the underlying signal so that it has been converted in the time frequency domain. But in other applications, actually the noise is attached to the image or the data set itself. So essentially that is the main difference. These are the main differences, and there are more. But what I want to say is it is kind of similar, but different topics. And when m is greater than 1, that is, you have more multiple components. Okay, and this is the example. The top red one and the blue one are two oscillatory examples that I simulate. The black one is the summation of these two signals. And you can see that as a time frequency representation. And there are two arrows you see here, right? If I still consider at each time the local maxima, then what will you get? You will see that, hey, over this region, we will get this guy to be larger. But in the beginning, I will get this low frequency part to be larger, right? So a so-called ridge will behave like this, starting from here, and at some point, it will jump to the other 9. But as I told you, there are two components inside. Two components inside. So using one ridge to describe it may not be reasonable, isn't it? Okay, so I superimpose the ground truth. The black lines are the true instantaneous frequency. The red line is the middle, the mean of these two curves. And the definition we propose, look, this is the proposal. I don't claim it is the best one. You may come out with a better definition, but based on the practical experience, this seems to be a reasonable definition. Okay, I say that I will define ridge in exactly the same way as before. That is, at each time, I try to find local maxima, but when I find local maxima, I will focus on different subbands. For example, for the first component, low frequency component, I will focus on this band. For high frequency component, I will focus on this band. That will be the assumption. And you determine the ridge. So that is how we call it the ridge. So in the end, when there are more than one oscillatory component, okay, the ridge is actually a set value function. That is, there are multiple ridges on the time frequency domain, not just one. So you can see the ridge is roughly the instantaneous frequency, or it should be B2, B1, okay, whatever. And we have similar theorems describing that. Okay, in the end of the day, the ridge gives you the inverse instantaneous frequency information, and something similar to before. Okay, so far good. Where is noise? Where is noise? I don't say noise at all up to now, right? So let's see noise. I give you exactly the same signal on the top. And now I add some noise. And this time the noise is super simple, just Gaussian, stationary, nothing crazy. So don't overthink about it, just ordinary noise. I sum them and I get one realization of this random process on the third row. That is what I have. Now I run continuous wearable transform like before. This is how the time frequency representation looks like, how it looks like. Isn't this beautiful? You see, there are some kind of crazy bubbles and something on the background, and there is some kind of curve. And you have seen the ground truth, so you know, hey, our eyes are very good. We know there is some component, right? We are happy about it. But should we? Can we just use exactly the same definition of ridge like before to study this kind of data or this kind of transform? Can we? Or what do we really get? And I circled 3 places here to call your attention because those will be the places that are interesting. Let's take a deeper look. Counting, we are doing ridge, which is local maxima, right? So why do you want to plot the time frequency representation in that complicated way? How about if we just plot the local maxima? Maybe there'll be more informative. Yes, you are right. It is. Suppose now I don't plot signal on the top way, but instead, locally at each time, I just plot, find all local maxima. That is, the gradient is 0, okay? And the second derivative is non-negative. Sorry, is negative. And if there is 1, then I just plot 1 point. Okay, so this is the result. So this is a local maxima plot. Now, do you see anything interesting? Here, the red curve is the true instantaneous frequency. Oh, no, sorry, this is SF. So the red line is the clean signals ridge. And now, over here, do you see something interesting? The curve is continuous, but there is a discontinuity in the local maximum. There seem to have some jump here. And you can see some jumps here again. And this one, right, this part seems to have a jump, but it doesn't really jump out, still like continuous. So in the end, you see, hey, look, when you talk about ridges under the noise setup, actually sometimes the continuity assumption holds. We even don't know if it's C1, but at least it's C0. But here, over these 2 pieces, the C1, even C0 condition is not satisfied. So if you use local maxima to define ridge, you run into several troubles. First, well, look, there are so many things. So, well, maybe global maxima, right? Oh, well, yeah, great maxima. Global maxima is good. Yeah, let's use global maxima. But then, what is this? Huh? What? Yeah, well, there are kind of challenges here. Okay, so that is actually the challenge we encountered for a long time, and we haven't had, we didn't have too much good explanation or solution, and without understanding it, I jumped directly to design algorithms to extract ridge. And at some moment, I say, oh, I have to understand how good the ridge extraction algorithm is, and I don't know how to do analysis. And I come back. And we found, oh, this is actually more interesting than we thought. So, how to define ridge? Before I give you a definition, let me quickly go through some assumptions. For example, we will say, as I mentioned, phi is a kind of very nice Gaussian random process. We even assume it is continuous. Very good. And you have the covariance, which has the density function. Everything is perfect. We don't assume anything crazy. And we even assume, hey, the mean of the random process is 0, because Waverly transform doesn't have support at 0, so everything constant will be killed. So there's no difference if a random process has mean 0 or not. So mean 0. And you can show that the random process can have this spatial representation, square root of p times z, which is a Gaussian random measure. And now you have the Webley transform, which is nothing but the low-pass filter, oh, sorry, bandpass filter version of phi. Very easy to see it. So this is our assumption. We will put assumptions on psi and p in a bit so that we know we have a full quantification of noise. And this is a remark, as I mentioned, you can consider more general random processes, but the analysis is more challenging, but it will not give you any further insights about reach. So let's be satisfied about stationary. Okay, I admit I'm lazy. So, okay. So now the second assumption is about mother wavelet. So we say that the mother wavelet in the frequency domain is unimodular. Okay, you can always assume or consider some crazy wavelet. In the frequency domain, it has a flat head and so on. Then what is reach? What do you mean by reach? Then I don't know how to define it. So unimodular, only one point. Okay, and the side head is C3 with sufficient decay conditions, which I put here, but you don't need to worry about all these conditions. You can just imagine everything I will talk about is Schwartz. Okay, decay very, very fast, and it doesn't touch zero. There's nothing to worry about. Okay, for technology, doesn't really help too much for the reach understanding. So we immediately have this theorem, which you can show, and it's maybe easy to see because it's a bandpass filter already. The Webley transform is actually C2. Okay, you have sufficient regularity, so you are allowed to take derivative to do everything and so on, which is very good, almost surely. And then the further assumption is about the spectral density function. We will say that spectral density function will decay sufficiently fast to the infinite. That is, we assume there is no crazy high frequency noise. And that echoes the original assumption that the Gaussian random process is continuous. Okay, and if it is a really white noise, for example, or pink noise, the spectrum is flat or even polynomially increasing, well, we are trying to bypass it, but not yet, not yet. Okay, and then another assumption is near zero, which describes a long tail dependence, long range dependence structure. And we assume that either you have some kind of long range dependence or short range dependence. Both are fine. You can just choose one. And but if it is long range, then we need to put some assumptions of how the spectrum blows up at frequency zero. And if you make this assumption, then you can prove something very intuitive. That is, well, because the spectrum, the noise doesn't have crazy high frequency information, right? So when scale goes to zero, the Webley transform will go to zero. Okay, and the other thing is because you do not have any crazy long range dependence, so the mean will go to zero. That is when scale becomes infinite. Okay, you will still get zero as well. Okay, and this is almost surely. So which is good. So we now know how to control. First is C2, and when scale goes to infinite, it is zero. When scale goes to zero, it is zero. So we have everything well controlled. You can even prove that this kind of continuous Webley transform, continuous Webley transform, yes. If you do some proper weighting, it will be holomorphic on the complex domain, but that is not our focus today. Now, what is reach? I have the sufficient definition. So the definition is very simple. As I told you, the regularity assumption might be too much. So we simply put this as a definition. It is a scalegram of the random process, and at each time I find argument. So in the end, the so-called reach under this assumption is the graph of a function which might be multi-valued, because look at this picture. At each time, when I say global maxima, how can you guarantee that there will only be one global maxima? right? I cannot, in general. That is what we need to prove. We need to prove that under some conditions, yes, it is true. But just giving you a random process, at least I don't know how to say so. Okay, second, what is a regularity? I have told you there will be some discontinuity, but how much regularity can you guarantee so that we can justify the algorithms we design that I will explain to you in a bit. And when there is a multiple component setup, for example, you have more than one oscillatory component, then actually we define in the same way using the same band.